Right. Well, let's, in the interest of time, start. So please go ahead.
So I start?
Please.
Okay, so thank you. In the next 15 minutes, I will discuss about the modeling of regional subduction, such as Andean type subduction to global plate tectonic. This is part of the strategy group and also of the MIT project of my postdoc. So first, I will introduce you to the tectonic context of the Andes and show you that in that area, we have run two different type of model, a 2D model of the Central Andes and the 3D model of the Southern Central Andes using the aspect code. So the magnitude of shortening in the Andes is strongly controlled by the amount of sediments bringing water into the subduction interface. And in Central Andes, where there is almost no sediment, has been estimated to 0.05. And we have a shortening magnitude in the order of 300 to 400 kilometers. While in the southern Central Andes, where we have about 1 to 2 kilometers of sediments into the trench, the friction coefficient is in the order of less than 0.02. And so I will discuss about the effect of sediments on global plate tectonics later. Another feature that is important to discuss is the subduction of the Juan Fernandez hotspot ridge from Central Andes around 35 million years ago, and its migration of Central Andes at present day around Sierras Pampeanas latitude, 33 degrees south, and due to the obliquity of the convergence between the plate. And with that migration of the flattening slab, the so-called Pompeian flat slab in the I make a cross-section going through the Central Andes, and you can see the subduction of the oceanic Nazca plate under the South American plate. The South American plate can be splitted in two different domains: a plateau domain that show not too much deformation at the surface, but a strongly delaminated mantle lithosphere beneath, and a foreland domain with hosting of the Brazilian cratonic shield and the intense deformation into the Eastern Cordillera and the Subandean ranges. So you can see here the shortening rate that show how the shortening has been changing and varying over time. And we were interested in understanding what controlled the pulse of shortening rate in the last 15 million years. And for that, we have set first a 2D model of the Central Andes prescribe first the velocity to initiate the subduction, but also an oceanic buoyant plateau in order to get the flat subduction, a flat subduction that's similar to the one of the Southern Central Andes at present day. And then we open the left boundary and we let the subduction evolve under its one buoyancy while we keep pushing the South American plate. And so one of the main driving force of the shortening of the Andes is the absolute velocity of the South American plate towards the trench. So we wanted to test keeping the same friction coefficient at subduction interface for Central Andes 0.05, different results from using some prescribing different velocity for the overriding plate. So you can see here that that with a 4 centimeter. So first we have the flat subduction and the steepening lead to the delamination of the mantle lithosphere. And with 4 centimeters per year for the overriding plate velocity, we see that the slab is not deforming at the mantle transition zone, while with 1 centimeter per year is strongly deforming and lead to much less deformation and no undertrusting of the Brazilian cratonic shield. And those subduction regimes, they are maybe similar of some phenomena that you experience in your quotidian life. You apply some tooth on your brush or when you pour some honey on your toast. The lateral velocity at which you pour those different viscous fluid will lead to different way of deforming those fluid. And so here I take back the geological data compilation from the beginning of that presentation. And I can plot the shortening rate from the so-called slab anchoring model with 4 centimeters per year for the overriding plate velocity. That shows that we are overshooting the shortening rate, most of the model. And I can also plot the 1 centimeter per year, which is the piling, and which shows that we are underestimating the shortening rate. In all of the model, we are always overestimating the shortening following the flat slab steepening. But the model with 2 centimeters per year, which correspond also to the average velocity of the overriding plate over the last 30 million years, seems to predict those pulses of shortening rate that we observe in the last 15 million years. Splitted into the shortening rate of the plateau domain and the one of the fallen domain to see that the pulse at 15 million years correspond to first shortening from the eastern Cordillera, the eastern part of the plateau domain, but also the initiation of the underthrusting of the Brazilian tectonic shield. And we can associate to this shortening rate a different stage of subduction dynamics. And we see that most of the pulse are happening when the slab is steepening into the upper mantle, which lead to the blocking of the trench. And when the trench is blocked and the South American plate continue to advance toward the trench, the difference is accommodated by the shortening of the Andes. In terms of we can see that the model predict a growth of around 13 million years, which is about the time where the Brazilian cratonic shield underthrusting become proeminent. So what about the present day where the flat slab is currently there? So here is a picture of the southern central Andes, and you can see the blue part showing the place where we have the flat subduction. And you can see that in that area, like the strain is quite distant. And you uplift the crust, forming a crustal uplifted blocks far from the main orogen. And so to build this model, we have first built a lithosphere model of the area where we have constrained the density using gravity, as well as the thickness of the different layer of the lithosphere, and later on the thermal state of the lithosphere. And this was the main work of Constanza Rodriguez Piceda during her PhD. And so we have implemented those different data into aspect to build a driven model of the area. And we then prescribe the plate velocity from the east and the west, and we run the model for a short time. And this allows us to take into account the whole heterogeneities in terms of strength of the area. And you can see that on top of the flat slab, the lithosphere is quite strong due to the cooling from the flat slab. But on top of the steep slab, the lithosphere is quite weak. And so if we look at the resulting strain deformation at the surface, we can see that on top of the flat slab, the strain rate is accumulating in front of the flat slab. So the stress is transmitted at the front. This is what has been called the so-called slab bulldozing, but then we can see different. So in the southern part, the deformation localized in front of the orogen in the foreland, following the so-called thin skin deformation style, as seen in the field, but also on top of the shallow slab, the deformation is distributed as we have seen in the previous picture, and at the place where we have those uplifted crystal block. And following the fixed skin deformation style of the foreland. And so we interpret this deformation as a transpressional deformation that comes from the shallowing of the flat slab and uplift, and therefore distribute the deformation and uplift those crystal blocks. But what about the effect of sediments into global plate tectonic? Here you can see from this picture on the right from the paper of Sobolev and Brown 2019 that a friction coefficient, an effective friction coefficient of 0.03 at subduction channel seems to be able to retrieve the global plate velocity, the first order global plate velocity. But this friction coefficient of 0.03 at present day, it might not have been the same 1 billion years ago or in other times. And so here is a figure, figures that show you some estimation, a relative estimation of the sediments in the trench, where the sediments in the trench have been accumulating faster following a major glaciation, which would have lubricated the plate interface, lead to faster subduction potentially, rollback, and fragmentation of the continents, and the formation of more passive margin. But so we want to test this hypothesis. So we tested. So we set two different global model to account the distribution of the continent of Rodinia at 1 billion years, and we changed the friction coefficient of the mantle as a proxy, which correspond to the oceanic domain from 0.05 to one model in 0.05 and another one is 0.03. And you can see that at the beginning, the plumes are reaching from the surface, and we quickly connect those different subductions to form major subduction zones and the global plate tectonic with the model with friction of 0.03, such as present day. But it's the friction of 0.05, we form small-scale regional subduction zones, but not so much stronger global, not so much important global tectonic. And this can be seen from the mobility, which is a ratio of the surface velocity by the global tectonic, and which shows us that in the model with friction 0.03, the model is mostly driven by subduction, so subduction-driven plate tectonic, while in the model with 0.05, the model is mostly mantle-driven plate tectonic. And so what happened quickly over depth, so we have the plume reaching the surface in this model and forming circular subduction here in blue. And then the strain localized along one side of the circular subduction until the strain connect together to form a large plate boundaries. So this is a bit of still a work in progress, and now the current step of this model will be to implement more fancy strain rheologies, such as damage strain weakening rheologies, in order to localize the strain, have less distributed strain in this global model, and localize it around riftings, dorsals, and plate boundaries, but also finalizing the coupling of the FastCape CC with the sphere with FastCape, so we could take into account this, we could weaken the rheology whether we have sediments or not. And to finish, I let you with this rendering of this aspect global model into Unreal Engine that I did on my as a hobby. Thank you. I cannot hear you, Menno.
All right, sorry. Yeah, thank you very much. Great presentation. Okay, then I suggest we'll move on to next speaker or set speaker, Agnes Kiraly and Yijun Wang. There you go. I can't hear you.
Sorry, I couldn't find the Zoom thing anymore. Okay, do you see the right view of the presentation?
I see a presentation view, yes.
Cool. Okay. Hello, everyone. We decided to do this presentation together with Yijun, who is my PhD student, because I'm gonna present a little bit more on like background on anisotropic viscosity and like the method that we have been working on And Yijun will talk a little bit about like how things are going in with implementing things into aspects. So a very quick intro about anisotropy and anisotropic viscosity. Anisotropy means that the material property is direction dependent. And when we talk about anisotropic viscosity, it means that the viscosity depends on the direction of the stress when shearing or deforming the mantle, for example. Anisotropy can be due to two different properties. One is often referred to as shape-preferred orientation, which means that there are layering of different quality of materials. And this can happen from microscale to large-scale layering. And then the other part, which is more interesting for us when we're talking about mantle dynamics, is the lattice or crystallographic preferred orientation of crystals that have intrinsic properties that are anisotropic. So olivine, for example, is very much an anisotropic crystal, which means that it deforms much faster when the strain direction is aligned with the olivine A-axis versus when it's aligned with the olivine C-axis. But obviously on large scale, this only can be observed and can have an effect when many grains are aligned with each other. And this is what we refer to as lattice preferred orientation, which happens due to deformation in the rocks. And due to formation, there are like sub-grain rotations of the grains, where the olivine A-axis tend to align with the shear direction. And then this is something that we can, for example, observe by shear rate splitting or seismic anisotropic methods. The good thing is that this LPO development for olivines and mantle rocks are already implemented into aspect thanks to the work of Mano and Magali Villen. And so we really heavily rely on this, even though that Yijun has found that there are some differences between the numerical method that we used to use for texture development of various directs, but it's just a model, so it doesn't, like, we don't know which one is the best, really. Okay, so in sense of viscosity, what does anisotropic viscosity mean? We know that, like, in general, we define the Pons equation between stress. It's shown here. But when we think about anisotropic viscosity, then we have to think about a tensor that describes the viscosity. And this tensor is a rank 4 tensor, which means that it would have 81 components. But due to the symmetry of both the deviatoric stress and the strain rate tensor, and this 81 components decreases to 36, and because of like time reversibility, it's actually reduced to 21 components. So we actually have to be able to like model anisotropic viscosity related to olivine LPO. We have to find this entire all the components of this tensor, and the difficulty in it is really that this viscosity is not just temperature and pressure dependent, but it is a nonlinear viscosity with some amount of grain size dependency. Previously, because it's not very easy to recover all these viscosity components, anisotropic viscosity has been modeled with some simplifications, and the most common one was using transverse isotropy, where you basically reduce the number of different viscosity parameters to 2, which is a normal and a shear viscosity, and maybe an angle that describes the angle of the easy slip plane with respect to your coordinate system. And then you can add to this the so-called director method, where you can add vector directors that describe the easy slip direction, and advect them and rotate them. And so this is what the of so this is showing like Rayleigh-Taylor instability, lithosphere and dipping layering, and because in the two anisotropic model we have a shear viscosity that's lower, much faster instabilities. Pink texture, you would have also small different abilities. Now, this is very nice, but this is not really capturing how olivine LPO-related anisotropic viscosity can affect geodynamic processes, because we don't really vary the strength of anisotropy over time, and we also disregard the third dimension, which might be able to add to it. But the most important part is that anisotropic viscosity is not as strong when you have a weak texture versus when you have a strong texture. So when many of the olivine grains are aligned, then it has a huge effect on shearing it, the easy slip texture versus across it. And so we tried to figure out how to recover all these viscosity components using micromechanical models of olivine anisotropy, which I failed very badly. But now the good thing that we learned since then is that if we rotate our reference frame into the reference frame of the LPO, which means that the mean direction of the olivine A-axis is aligned with the X direction and so on, then the viscosity tensor will have an orthotropic symmetry, and we only have to look for these few values. And this has been shown by the group of Montpellier, that you can actually reverse this and use the so-called heel yield plasticity to take out the stress dependency of the viscosity, or in this case, because we invert everything, here we have like the strain rate equal to fluidity times stress. But the point is that the stress dependency can be taken out using this heel stress, which is very similar to the equivalent stress, but it is dependent on the anisotropy of the texture. And then there is this A tensor, which is the anisotropy tensor, which is a material constant that's only dependent on the lattice preferred orientation, like so on the texture basically. And so what we really need to do is to find these what we often refer to as heel coefficients. And so what I have been working on lately is to try to find an easy way to recover these heel coefficients directly from texture parameters, because otherwise to actually find these like 6 parameters, you have to run these micromechanical models many times to then do like some minimum fitting of like to find these heel coefficients. So what I did is used many textures, like over 10,000 textures based on that have occurred in geodynamic models, and then applied this micromechanical model many times on each of them, find the best fitting heel coefficients for each textures, and then took out some texture parameters that we got from the mean orientation tensor of each texture. So we take the eigenvalues of each of these orientation tensors and use some linear regression model to each of these 6 parameters from the texture parameters. And so we got like really good fits, and then trying it out again in the geodynamic model created textures, it seems to be doing an okay job. So then we are confident enough that this is a good way to move forward. And then now I give the word to Yijun.
Yeah, so how we are trying to implement anisotropic viscosity into aspect is that we are creating this material model called LPO-AB3D into aspect. And this is currently just in my branch and it's not in the main aspect yet. What we do is that we track the olivine texture LPO on the particles. We interpolate the eigenvalues and eigenvectors, which are just textures, parameters that describe the mean orientation matrix to the compositional fields. And we also calculate the Hill's coefficients mentioned before. From those Hill's coefficients, we're able to get a scalar viscosity and also an anisotropic tensor, which we call the stress strain director in the aspect. And in the end, we apply the anisotropic tensor in the Stokes solver. So first, for this material model, we need to have an input that's the coefficients for calculating the Hill's parameters, the FG, H, LMN, the 6 numbers. For example, the equation here we have is to calculate F. We need 9 coefficients and 1 intercept multiplied by the eigenvalues of the olivine texture matrix. These coefficients we got from the linear regression model that best fits the textures we mentioned before. And it is very easy to update the regression model to obtain new coefficients and even new equations. And these are easy to change in the future if we have a better idea. And then we have the prescribed field outputting aspect to store and access the stress strain director, which is the anisotropy tensor. At the beginning of the iteration, we compute an anisotropic stress using the stress strain director. And at the end of the iteration, we save the anisotropy tensor into this prescribed field output. And also we use eigenvectors and eigenvalues into the compositional fields. With the eigenvalues we use to compute the Hill's parameters, and the eigenvectors we use it to the rotation matrix to rotate between the CPU reference frame and the model reference frame. The reason we need this rotation matrix is because that our constitutive equation using the Hill's parameters works only in the CPU reference frame, but we also need to rotate the CPU reference frame back into the model reference frame in aspect, so that we need a RCPO rotation matrix and the RCPOK rotation matrix, which we constructed from the eigenvectors stored in the composition matrix. So in the end, our anisotropic viscosity tensor, what is our anisotropic viscosity tensor? As you can see in this long equation, the part in the inverse of the part in the red rectangle is the scalar viscosity, and the inverse of the equation in the green rectangle is the anisotropy tensor. So where we are in our testing stage is that we have a shear box model. We are able to visualize the components of the anisotropy tensor and anisotropy stress. But what we really want to have is to be able to start the model with an initial texture, and this will be our ongoing work for the next week's Geodynamic World Builder Hackathon. We're planning to implement initial texture either by give it an input file, by generate random distribution of textures, or we hope to figure out how to generate olivine textures on a number of grains by using Bingham statistics. And we are also going to implement textures on the particles in aspect, so that when new particles are added to the mesh, they don't start with a random texture, rather they can start with whether the textures on the new particles can be interpolated from nearby particles that already existed in the mesh. And that's where we are on implementing anisotropic viscosity into aspect now.
Yeah, we don't have a thank you slide. Sorry.
All right. Thanks a lot for this presentation. Then I guess we'll open it up for questions. Are there any questions for either speaker? Renee?
Yeah, thank you. I have questions for both again, but let's start with Agi and Yijun. So you mentioned that the coefficients, so in several places you mentioned that you might have to start with random combinations of textures, or you have to interpolate texture from different particles to a new place. Are there combinations of these values that can be dangerous for the stability of the model? So I'm asking because I remember from working with the director method that it's possible to accidentally have essentially a zero viscosity in some direction, or even a negative viscosity in some direction, which would probably destroy the solver convergence and any hope of solving the equations. Is there a way to prevent that with this with the Hills coefficients?
So yes, kind of. When I'm searching for the Hill coefficients in this like database, I think like criteria. So the M, N, and L components, which are like in the basically the shear related anisotropic components, they always have to be positive. With the other three, it has to be only one can be negative and the other two has to be positive. So this is something that we can definitely put like as a asset, and I didn't have any problems with that at all. The question is more with the interpolation, is that can we use the eigenvalues and eigenvectors of the mean orientations, or the ones that we interpolate in the composition field, to then create new particles if there is like a mesh refinement, or there is a particle like, or like a cell that doesn't have a particle in it.
Yeah, I think that's something that we probably need to talk about, because currently you can either initialize new particles with a fixed value that you prescribe in the property, or you can interpolate the properties from surrounding particles, but then it will just interpolate the individual components, whatever data is actually stored on the particles. You cannot interpolate some derived quantity and then use that derived quantity to initialize the particles.
Yeah, I don't know how to. Yeah, I don't know how to do it yet, but I think that would be important to figure out.
Yeah, I mean, that's an implementation question that we can talk about. And Michael, I wanted to ask you, you mentioned that you have you developed this global plate tectonics in some of the models for a low friction coefficient of 0.03, but not with the other one. And you showed this mobility plot, but it looked like both of the models moved towards a mobility of 1. Is it true that like your plate tectonics still stalls after a while?
Yeah, I think that's an interesting thing. This is why also I want to have strain rate weakening rheology or something like this. I think the strain become distributed at some point and things kind of stall, and so they kind of like both like are going toward 1 around 600 million years. So, but I don't think this would happen if we properly solve the plate boundaries. So yeah, that's a work in progress.
Okay, cool. So you mentioned that you want to implement the strain damage rheology suggested by Lucas Fuchs in his paper. Did you check the strain weakening and healing that we already have in Aspect? I know Erin Heilmann implemented that a few years ago, and she worked in the same group. So I'm wondering how different that is from what we already have.
Yeah, so the strain healing I think is working with depending on temperature, and in the damage strain we want to be able also to recover some in a much more, I think, simplified way, like also like the strain from plastic domain. So just by having some kind of relaxation of the damage over time, using some kind of relaxation time. And so this will be a kind of an in-between between strain rate weakening and plastic strain weakening. So where we could just accumulate record like the accumulated strain over time, but also being able to relax it.
I think I see where you're going. Maybe check the strain dependent rheology model. It might be different from what from the Fuchs publication, but something like it exists, and maybe it helps to use that as a starting point to then implement the other version.
Yeah, right. So I'm actually right now currently running some tests with just strain rate reckoning. Maybe then I will add strain healing, and then and also beside, I'm building this different. Trying to implement this different rheology, but I'm doing that in parallel. Yeah.
Yeah. Okay. Awesome. Thank you.
Thanks.
All right, Matthias.
Hi, Mika. Nice to hear your presentation, and also nice to see your new models, global models. I have one question, and it's also kind of related with Derek's presentation. What about the sediments in the trench? Because as Derek showed, probably if you have so much sediments, it could also like you will have buoyancy and then slow down the action. So can you like test also that possibility in your models?
Thanks for the question. I think one of the main reasons why the sediments are too buoyant and lead to the plates that slow down is because in the study of Silvia Brizzi, there was no phase transition. So the sediments were not getting denser over time. There was no eclogitization. I had some model where I didn't have this phase transition, and indeed it was getting a bit slower. But as soon as you add those phase transitions, then eclogitization is an increase of 450 kilogram per meter cubic of density for those sediments. Well, obviously it will depend on the fraction of eclogite, but this will be much enough, in my opinion, to lead to a plate accelerating and not plates slowing down. But we are currently like running some subduction model also with some collaborators where we try to test the effect of sediments at a subduction interface, and how this results in a different shear stress and so on in the case, and we try to see if this works in the case of the Andes as a study case. Yeah.
Thank you.
Thanks.
All right. Are there any other questions? René?
I mean, if we have time, you mentioned that SPO is often ignored or not as commonly investigated for anisotropic viscosity models. Is there a reason? I never quite understood why.
No, actually, it's the opposite. SPO is way more investigated because basically this director method and the transverse isotropy is mostly representing SPO. So that's basically all the models are are using that. But for so that's great when you have like like dike sheets in the crust, for example. That's for example, or in the lithospheric mantle as well. But in the this is what Manuela Facenda did for the lower mantle for when they modeled like some anisotropic viscosity in the lower mantle, where there is like I think based on like how melt like like based on like micro structures, but yeah, either for like upper mantle, it's not. We are like only LPO related anisotropic.
Okay, is that because we don't know of any mechanism that would form this type of anisotropy in the upper mantle or in the mantle, or
yeah, well,
I'm just trying to get a sense of like
I
the relative
think-
importance of the
good
two
question.
mechanisms.
Yeah, I think in the upper mantle, or like in the asthenosphere at least, there is not really anyone talking about it. So I guess
We assume that everything is well enough mixed that we don't see
I
these
think so.
shapes.
Yeah.
Okay.
Yeah. I mean, it is possible that like on a microscope there is something, but I also think that the LPO related anisotropy is probably stronger, can be stronger maybe, but I'm not sure.
Mm-hmm.
In the lithosphere itself, I think SPO can be very relevant.
Okay, thanks.
Any other questions for the speakers? All right. Well, we have 3 minutes left until next session, so I think we'll just be moving on. It makes the most sense. So our next speaker in short presentation section 2, or the third one, is Juliane Dannberg. Can you share the screen?
Yes.
Great. Well, take it away.
Oh, wait, why is this presentation mode? Does someone know how I can change this to full screen? Oh wait, I have to.
Try.
Yeah.
There should be like 2 arrows that switch things around. Maybe display setting. If you click on that, that should be like presenters view.
Yes. Okay, yeah, I didn't see it because of the Zoom. Let me also just hide the. Oh yeah, this works. Okay, thank you. Okay, yeah, so I want to talk about changes in core mantle boundary heat flux through the supercontinent cycle and how that might affect the geodynamo. And so, yeah, so this is work I did with Renee and with Dan Tellner and Fritz Lecomte and Courtney Sprain. And so Fred nicely set this up, talking about the LLSVPs and all of the observations we have for the present day, so I don't have to introduce that anymore. And so here we see sort of an image of the LLSVPs where they are seen in tomography, shown in red. And we also see observations of hotspot locations at the Earth's surface shown in these yellow stars, and then the reconstructed eruption sites of longitudinous provinces as these green circles. And so we can see that these hotspots in longitudinous provinces seem to cluster around the LLSVPs. And that's not just the case for today, that's also the case for the past, because some of these longitudinous provinces are 100 or a bit more than 100 million years old. And so that has led to the idea, well, maybe these LLSVPs have been stable features, at least for that time frame. But on the other hand, if we look at geodynamic models, they tell us a really different story. So specifically, time-dependent geodynamic models can only reproduce the location of these LLSVPs if they prescribe a plate reconstruction as the surface boundary conditions for the velocity. And so then these plates, as they are subducted, they push around the hot material at the core, moved into the space, see the LLSVPs today. So this is the first paper that showed this, where in the top row we see a seismic tomography model, and the red colors show the slow velocities, so the LLSVPs. And then the bottom row is from the geodynamic model of that study from McNamara and Zhang. And the red colors show the hot and dense material at the core mantle boundary, and we see that those are sort of in roughly the same places. And it's sort of a contradiction. So we wanted to look at sort of how does this structure of the core mantle boundary evolve throughout the supercontinent cycle, And specifically, we wanted to focus on the heat flux across the cometer boundary because that affects the Earth's magnetic field. And so to do that, we set up 3D models and aspects, so these 3D global spherical convection models. And we also prescribed a plate reconstruction for the last 1 billion years as surface boundary condition for the velocity. So that's the one we see here on the right from Meredith et al. And then to compute all of the material properties, we used a mineral physics database. And so we assumed there's a dense basal layer in the mantle that's made out of basalt. And then the rest of the mantle is a mixture of basalt and Harzburgite. And so specifically, I wanted to talk about a few of the model parameters because we varied a few of them. So on the one hand, we tried a model that did not have this basaltic layer, so which I will call here the thermal model because it has no chemical heterogeneities. Another parameter, so like all of the parameters we changed have to do with what happens with the heat flux at the cometer boundary. So another one is the profile of the thermal conductivity, which is what we see here on the left. So in most models I've seen, the thermal conductivity or the diffusivity is assumed to be constant throughout the whole mantle. But like actually it would depend on temperature and pressure. And so what we've implemented for that in aspect is a depth dependent profile for the thermal conductivity that also depends on temperature. And that increases the conductivity at the cometer boundary by a lot. And then the third thing we changed is the viscosity near the cometer boundary. So in general, we used this viscosity profile from Steinberger and Calderwood here on the right. And then we tried different scenarios where in one scenario, we made post-perovskite 100 times weaker. And then in the other one, we made our basaltic layer 10 times stronger. And so this is sort of in the, so I didn't know about Fred's results when I set this up, but sort of it's the same idea that we see sort of both of these would make the piles stronger than the surrounding. And so that leaves us sort of with these 5 different models where we can look at sort of what is the pattern of the heat flux at the cometer boundary. And so let's look at the evolution of one of these models. So what we see here, so the 2 sides are the 2 African and Pacific hemispheres. What we see in these blue colors is subducted cold material moving down into the mantle, where sort of the darker the blue, the deeper the depth. And then these yellow to orange colors, this is the dense basaltic material at the cometer boundary. And so the more orange the colors, the higher the topography above the cometer boundary. And then the red, sort of the red stripes at the surface, those are the regions of high deformation at the surface. So those are the plate boundaries. And we can see that basically wherever the plates are located, but later we see the cold downwellings from the subduction zones going down into the mantle. And we can also see that they then push this hot basaltic material at the cometer boundary out of the way and shape that into these piles. And so the first thing we wanted to do was to make sure, well, like do these, like if we run these models to the present day, do they compare, like how do they compare to what we see from the seismic tomography? And so that's what we see here. So I show 3 different models that we run, where the background colors show the temperature. So red is hot, cold. And then in the bottom right, we see an example for a seismic tomography model. So that's the CMB model. And all of these are slices in 2,600 kilometers depth. And so here, red is slow and blue is fast. And then for all of these other panels, I've also added as an overlay in yellow wherever we have slow velocities in the tomography. And what we can see is that in the models that do have this basaltic layer at the base, we do get a somewhat reasonable agreement between where we have the slow regions in the tomography and the hot regions in our models. But in the model that doesn't have this dense layer at the base, the patterns look really different. And so there's really not a good agreement. So in the following, I will only talk about the models that do have this dense layer. And right, of course, this is just sort of, it's not a proper comparison. We didn't try to get the best fit to the tomography model. It's just sort of a check. Oh, do our models look reasonable? Do they make sense? So then what we were interested in was the heat flux pattern at the cometer boundary and how that would change through time. And so that's what we see here for the thermochemical model. So the yellow colors show the regions of low heat flux out of the core. So those would be the hot regions. And we can also see the sort of small scale pattern within these regions. And so that's because the piles that form out of this hot material, they convect internally. And then all of the blue regions, those are the regions with high heat flux out of the core mantle boundary. So those are that's the cold subducted material. And what we can already see is that these heat flux patterns, they change a lot over time. And so in the next step, let's have a look at sort of how, like, what's the difference between these different models. Oh, so here, if we go from top to bottom, we go forward in time, and the different columns show these different scenarios for the model run. And so what we can see again through time, the pattern of the heat flux definitely changes. But if we compare the different models, so if we look at the different models within one row, the pattern doesn't depend a lot on sort of the model or the core mantle boundary. So you can see, even if we look at sort of the present day, we always get this sort of girdle of cold material, and the exact configuration is slightly different, but the pattern is sort of similar because by the plate reconstruction at the surface. But what is different between these different models is the heterogeneity of the heat flux. So sort of what's the amplitude of the heat flux, and what's the difference between the most and the least heat flux. So basically, if we have this pressure and temperature dependent conductivity, that means we have a higher conductivity at the core mantle boundary, so we can extract a lot more heat in the cold regions. So we have a higher amplitude here. And then also, if we have, in addition to that, if we also make post-perovskite weak, then we have it can deform much more easily, so we can have more convective heat flux. And so we also extract much more heat out of the core. And so now we specifically wanted to look more at where these patterns come from. And so for that, we can compare the heat flux pattern at the core mantle boundary to the configuration of the plates at the surface 200 million years before that. So that's approximately how long it takes for these plates, when they're subducted at the surface, to reach and affect what happens at the core mantle boundary. And so here in the plate configuration, these green colors are the continents, and these black lines, they show us where the subduction zones are located. And so what we can see is basically, if we compare these patterns, wherever we have subduction zones at the surface, if we then check 200 million years later at the core mantle boundary, that's where we get the cold material and the large heat flux. So for example, this subduction zone we see here, or this one we see here, or this subduction zone we also see as this blue patch. And we can look at this more quantitatively by computing a power spectrum of our heat flux pattern throughout time. So that's what we see here. The x-axis is the time, with going forward in time towards the right. And then the different colors are the powers of the first 4 spherical harmonics degrees of the heat flux pattern. So the dark blue is degree 1. So that means we would have one hot hemisphere and one cold hemisphere. The teal one is degree 2, which would be the situation like today, where we have these 2 hot piles and then a girdle of cold material in between, or the opposite, 2 cold patches and a hot girdle in between. And then the green and yellow are sort of to the higher degree, so they would be more short wavelength patterns. And so I've also annotated the stages in the supercontinent cycle here, so that we can see how things change throughout that cycle. And what we can see if we look at the present day, so today we have this dominant degree 2 pattern, which is also what we see in the observations of with the 2 LLSVPs. And so today we're also in this breakup stage of the supercontinent cycle. If we go further back in time, at some point we have degree 1 being the most dominant degree, and that's during the time where sort of we had a stable supercontinent. And then if we go further back, where we have these higher degrees, that's sort of between the breakup of Rodinia and then starting the assembly of Gondwana. And if we go even further back to the breakup of Rodinia, we also have this degree 2 pattern. And to understand why that happens, we can go back to our plate configuration and we can think about that. So if we think about today, today we are in the breakup phase of a supercontinent. And to break up a supercontinent, we need a ring of subduction zones around the continents to be able to do the breakup. So that means we would automatically get this ring of cold material at the cometer boundary, which would facilitate this degree 2 pattern. If we want to assemble a supercontinent, we need to have subduction zones between all of the terrains that are assembling the supercontinent. And so then we would tend to get a lot of cold material downwelling beneath the supercontinent while we have the supercontinent stable. So during the time of a stable supercontinent, we would expect cold material in the supercontinent hemisphere and a lot of hot material in the superocean hemisphere. So we would have this degree 1 pattern. And then if we have these sort of lots of different subduction zones in different places, or they change their location over time, then we would get this higher degree pattern. And so like some of these, like not all of these ideas are really new, but what we wanted to look at now is how does this change in heat flux pattern also affect the geodynamo? And since these talks are not long, and this is also still work in progress, I can just sort of give a sneak peek into some of our results. So the idea is we now take this pattern that we've computed here, and then so the geodynamo models run on a much shorter time scale. So we can fix some of these patterns and apply one pattern to a geodynamo simulations. And then we use the Leeds geodynamo code from Willis et al. To run these geodynamo simulations. And then these would predict a magnetic field at the Earth's surface and analyze this field to see, well, how Earth-like is the field, how does it compare to paleomagnetic data, but also how stable is the field in terms of things like how often does it reverse or how dipolar is the character of the field. And so as a very preliminary result, we've tried the 5 different patterns that I show here. And so it seems like the 2 patterns that I've marked in red, those are the ones where the magnetic field is more unstable than for the other ones. So it looks it reverses more often. It looks less dipolar. And so there are we're still working on why that could be the case. But one thing that we can see in these patterns is that those are patterns where we have sort of these large patches of really low heat flux out of the core. So basically almost a hemisphere or like large patches where we just have really hot material. And so now we're looking into sort of how exactly that is related. So to conclude, we've seen that the pattern of the heat flux at the cometer boundary changes over time, and it's driven by subduction. And then sort of how many, what's the number and morphology of these hot and dense structures at the cometer boundary, that depends on the stage in the supercontinent cycle. So if in the stable supercontinent phase, then we would have a degree or like that would facilitate with the supercontinent and the superocean. If we are in the that would be easy to form a degree turn with the subduction zones spread out or change location pattern. And so if you're interested in more of the details, so we did this to GGI, and so you can already look at the. Right, thank you.
Right, thank you very much. Our next speaker is Arushi. She's gonna continue talking about global models. So take it away.
Yeah, thank you. Again, I want to talk about Mantle models and how we integrate the data and develop these models. These are the models that are based off our previous study, which was published last year. And just to give you a brief motivation why we want to develop these models. So if we look at the available models that we have today, some of which I'm showing you here, the common feature which you can all see is the way the plate boundaries are incorporated. So all of these models, they use a very simplified plate boundary geometry, which is a novel model, and that came out over 20 years ago. And since then, not much work have been done, not been incorporated, or the effects of plate boundaries has not been utilized. So we want to use updated plate boundary geometry model. And additionally, these models also come at different results regarding what are the drive the plates. For example, to do it at the lower Mantle heterogeneity, about 70% to the plate driving forces, while Stadler's, the models presented by them, they suggest that if no lower mantle heterogeneity is present and only slab pull is present, that can explain most of the plate motions. So we resolved these and set up our models. And as I said, we want to integrate most of the recent available constraints. Specifically for the plate boundary geometry, we use a global earthquake model. And this is a model that is based off seismicity, but it has discrete zones, discrete weak zones in the oceanic regions. So all the regions that are in oceanic regions, they're very discrete. And if we look at the continents, it is forming more of a crustal depth shear zone. So it's a more diffuse deformation zones in the continental regions. For lithospheric structure, we use a TM1 model, and that incorporates the cooling of oceanic lithosphere and also different ages of the continental lithospheres. And below the lithosphere, we use a global tomography model, which is inverted from both P and S waves, and this is the Nathan Simon's model in 2016. And additionally, we also use slab 2 model to define our slabs. And this is something which is new in this study or in the current models we are developing, because we recognize that the slabs play a very important role, and we did not have the dipping slabs or well-resolved slabs in our previous models. So we use all these data to get our physical properties. So here I'm showing the viscosity distribution. And these viscosities, they are obtained from the temperatures that are converted from the tomography and the lithospheric structures. And additionally, we use geodynamic wall builder to prescribe weak zones or weak viscosities at locations that are taken from the global earthquake model. And we also scale all the lateral heterogeneities and viscosity to a 1D profile, which is modified from Becker's study in 2001. And I will discuss the motivation why how we changed that. So we set up, because we have different scales of deformation, we want to represent all these heterogeneity using adaptive mesh refinement, so that we have very high resolution near the surface, and specifically slabs, which are very well resolved. We use very high resolution so that the minimum cell size is about 8 kilometers. And our models are instantaneous, and we only solve for momentum and mass balance equations with prescribed temperatures. And all of these ingredients or all of these data types are implemented in a modular fashion in aspects, so that we can change these input tomography or input lithospheric structures, or if we want to use the slabs, or how much weaker we want these viscosities of plates to be. So we can all change that in modular fashion in aspects. So this is right now available in this cookbook. Because there are uncertainties in the rheological profile, we vary 3 parameters. First is the fault viscosity, that is the frictional forces that is along these plate boundaries, and that describes how easily the faults or how easily the plates can move with respect to each other. We also vary the asthenosphere viscosity, which defines how much easily the plates can drag at top of the asthenosphere. And additionally, we have another layer with respect to the Becker's profile, and that is the mid-mantle viscosity, which is a layer that extends from 660 kilometers until 1,000 kilometers. And we introduced this layer because when we did our initial test, our slabs were not able to transfer all the pull at the surface, and they got stuck. So we vary these parameters, and it describes how easily the slabs can pull the plates at the surface. And to quantify our models, we use RMS velocity residual, and that's also a post-processor in aspect. So let's look at some results. So here I'm showing you in each subplot a different model that corresponds to one combination of plate boundary geometry, plate boundary viscosity, and mid-mantle viscosity, but it's for one particular asthenosphere viscosity. So if we go from left to right, we have increasing plate boundary viscosity or more resistance for the plates to move with respect to each other. And from bottom to up, we have more resistance for the slabs to go down, or we are increasing the mid-mantle viscosity. Each of the subplots, the blue regions are the regions that are slower with respect to the GPS observed velocities, and red regions are the regions that are faster with respect to the GPS velocities. So as we would expect, if we go from left to right, we have increased resistance, so the plates become slower with respect to the observations. And same pattern is also observed if we go from bottom to up, because we have more resistance for the slabs to go down. So so there's less force available for the plates to be driven, and the plates have become slower. And the opposite pattern is observed if we reduce this resistance and if we go from top to bottom and left to right. So we try to calculate or quantify our RMS residual for each of these model parameter combinations. And what we find is that our best fit models have about low mid-mantle viscosity, about 1E20, and intermediate fault viscosity. But this is, again, for one particular asthenosphere viscosity value. So next we do the same study for different asthenosphere viscosity. And again, from left to right, we have models which have increasing asthenosphere viscosity, and within each subplot, these colors, they represent the RMS residual of the model velocity. So the darker the colors, the poorer is the fit. So for one value of asthenosphere viscosity, if we go from left to right, we have more resistance, and from bottom to up, we have more resistance for the slabs to go down. So the models which have good fit, they are lighter in color. And what we find through this parameter study is that the minimum RMS velocity which we observe with respect to the observations is about 1.6 centimeters per year, and has the rheological profile, which I'm showing you at the bottom right. Because the models are very fast, if we have low viscosity, both for the false and mid-mantle viscosity, these models have very high residuals also. But overall, we do find good models, and we can look in detail also. So this is our best fit model, which I just showed you here. But the colors here now represent the regions that are poorer fit with respect to the observations, and the lighter colors are the regions that have good fit with the observations. But because we also want to look at the contribution of slab pull, we do another model run which has no lower mantle heterogeneity or no tomography data, and it only has the lithospheric structure and the slabs. So on the right is the model that has no tomography data and only slabs and the lithospheric structure. So again, the darker colors are the regions that are poorer fit with respect to the observations. And what we see is that, as we would expect, that because there is less driving forces, the overall fit is poorer if we have no tomography. But if we look at these quantified measurables, the angular fit is still pretty good. And there are actually regions such as Eurasia, Europe, which fits better if we have no tomography data. But places like India and Australia, they are more influenced by the lower mantle tomography. So if we remove this lower mantle tomography, the fit becomes quite poorer. And overall, we see that 75% of the observations can be explained if we have no lower mantle tomography, but only slab pull to the slab 2 model. We also look at the strain rates from our models and compare that with the global strain rate model. And we identify 3 zones. So the first region is the discrete, very high shearing zones where the plate boundaries are. So these are the regions here represented by magenta and the red colors. So on the left is our modeled strain rates, and on the right are the observed strain rates. So the red and the magenta regions are the regions that are deforming a lot and has very high strain rates, and these are the regions that are at discrete plate boundaries in our model. And then we also have intermediate strain rates, and these are the regions that are at the more diffuse plate boundaries, for example, in the Indian Eurasian plate boundaries. And then we also have regions that have very low deformations, and these are the blue regions here in the model, but because there is no observations in the global strain rate data, it's the red regions here. And what we find is that, just to conclude, what I'm showing you is that we find improved fits from our previous model studies. And this is mostly because we are now using well-defined slabs from the slab 2 model. And our best fit plate boundary viscosity is about 2.5, and the asthenosphere viscosity is about 5E19. And if we look at just the contribution from slab pool, we get about 75% or 3/4 of the total plate driving forces. And if you notice, we have not included one big factor in our big driving force in our model, and that is from topography. So that is still work in progress, that we want to include topography from our model into our models. And we also want to include a more recent lithospheric structure into our models. So with that, I will conclude. Thank you.
Right. Thanks a lot. Great presentation. Are there any questions for either speaker? Yes, Anna.
Hi, they were both great talks, very interesting. I have a question for Arushi. First of all, I think it's awesome to see that some of that 75% of the plate motions can be assigned to the slab pool. That's something I found in regional models as well, the Eastern Mediterranean. So it's really cool to see that works in globally as well. But I was wondering whether you experimented with the fold, so the plate boundary fold width, because I guess that kind of trades off with the fold zone viscosity as well.
Yeah, we did experiment. So I should have mentioned that our refinement levels for the models I'm showing you is 4+4, so 4 global and 4 adaptive. And what we did try is using 4 global and 5 adaptive, and then reducing the plate boundary thickness, and then increasing the plate boundary viscosity. So we defined our models and then reduced the plate boundary thickness, and then also, let me see if I'm saying it, reduce the viscosity and reduce the thickness of the plate boundaries to get the similar strain rates, right? Yes. But I remember ratio was not 1:1, that if I reduce the plate boundary thickness by half and increase and reduce the viscosity by half, the observed velocities were not comparable. So I think it was something in between that I tried. Yeah.
All right, thanks.
Right, Aggie.
Hi, I have a question to Juliane. It was both of the presentations were really nice, but in the times when you have with the geodynamo, like more like unstable pattern, do you also have like lower intensity of the magnetic field?
So we didn't look at the intensity, and that's mainly because the intensity is something that's really hard to get from the paleomagnetic data. So what we looked at was, like specifically the 4 things I remembered that were different were sort of the time that the magnetic field spends reversing versus the time being stable. Then the dispersion of the dipole. So if you look at sort of, if you average the, so basically, if you plot the virtual axis of the dipole your field would have, sort of if that stays in one place or if that sort of moves around, then how dipolar the field is. And yeah, so like sort of those are all characteristics that where we can directly go back to paleomagnetic data and say, right, this is something that we can get from the paleomagnetic record and then compare it directly. And so that's why we only looked at those things, and I didn't actually look at the intensity. But right, that's right. If we only look at sort of the general mechanism, yes, that's something that we could also look at.
Yeah, because here at NAFAB, there are like 2 projects. One is like for the Devonian, and the other one is on the Ediacaran, like magnetic mass. And at least for the Devonian, the main like idea is that the magnetic field is just like super weak, and that could be like something related to. Yeah. But it's very cool. Yeah.
Thank you.
Right, Bernard.
Yes, I have 2 questions for Juliane. The one is, even you may be tired of this, do you think this much higher viscosity which Fred proposed, this could swing back from this degree 1 versus degree 2 towards degree 2 forever, or is that something because of the thermal viscosity lowering is still not enough to get the viscosity of the piles high enough. So I think you haven't done those calculations, but maybe you can have some outlook. And the second question is on true polar wonder, whether that's something you consider for applying the results to the core, because I mean, your calculations are in a Mantle reference frame, but on the other hand, maybe the subduction zones are input in a paleomagnetic reference frame. But I think this whole thing is a bit confusing. So maybe you can tell us a bit how you handle this. Thank you.
Okay, so for the first question, the more even more viscous piles. So I didn't know that when I ran the models that like maybe 100 or 1,000 times more viscous might be something that would be reasonable to try, but it's definitely something that would be very easy to do. And sort of my intuition is, so and then there's also a trade-off with the commented boundary temperature, obviously, right? So we picked 3,700 Kelvin because we thought that would be reasonable, but right, the hotter you make the commented boundary, the less viscous you make your piles, even if they're intrinsically more viscous. And if the commented boundary temperature is not as hot, then you can't make the piles really viscous, or basically you don't have as much of a trade-off. And so I think that it would depend on that as well. And if you have a high commented boundary temperature, I think that I think material could still deform easily on the 1 billion time scale to get into these piles. But I mean, of course, you could, you can always make the piles really viscous so that they don't deform. And then sort of the question I see is, you would have to figure out why did they get into this degree 2 pattern in the first place. So it would then have to be something about looking at sort of where does this material even come from? So for example, I guess it could only be primordial. So if you assume it's recycled material, but it's 1,000 times more viscous, it will never, or I don't see how it could easily accumulate in these piles and sort of segregate from a subducted slab because it would be so viscous. So you would then have to assume if it's intrinsically really viscous, it would be primordial. And then you would have to think about why would it have this degree 2 pattern from the start? And I think also going back to Fred's results, I think what he said is, it doesn't have to be that the piles are intrinsically dense. It could also just be everything that's around, or no, intrinsically viscous. It could also be that everything around the piles is just less viscous because it's post-perovskite. So that would also be something interesting to try. Right, do a combination of these where maybe the piles are 10 times intrinsically viscous, but then the surrounding is 100 times less viscous because there's post-perovskite. Right, that could also be a scenario that could work. So there's definitely a lot more scenarios we could test. And then the second, the reference frame. So we put in we take the original reference frame of the plate reconstruction, which is a paleomagnetic reference frame. And so then I just thought, well, then we just don't have to worry about true polar wonder at all, because it's already it's sort of the mantle does whatever it does in response to the plate reconstruction in whatever reference frame it's in. And so then we get the core mantle boundary heat flux already in the reference frame that's the correct reference frame for the geodynamo models. So we don't even have to we don't have to think about, for this study, we don't have to think about true polar wonder at all. And so that's why we also haven't looked at sort of how much would the mantle change with respect to the surface or any things like that. But it's I know there have been a few studies looking at this recently, and it would definitely be something that we could look at in our models. We just haven't done it so far.
Yeah, I mean, it would just be some kind of a sanity check to check whether the rotation axis or the axis of maximum geoid actually stays in the same direction as where you impose it. So that's something where then the geoid modeling would come in again. Yeah. Yep. But apart from that, I think if you use a paleomagnetic reference frame, this makes perfectly sense that you don't have to worry about it begin with. Thank you.
Thank you.
All right. Are there any other questions?
I have a question. I'm sorry. It's okay.
Then
maybe I can wait.
Well, oh yeah, sure. Anna, go ahead.
Yes. Okay. So I have a question for Arushi, no? So maybe a suggestion, no? So I remember that in the late 90s, there were these thin shell models by Peter Bird, and he compared his predictions not only with velocities, but also with horizontal principal stress directions. So he found that some models were good at fitting the velocities, but not the stress directions from the world stress map. So we talked about that in the AGU meeting with Arushi, no?
Yeah.
Yeah, you're right. You say that the problem is that the directions are very scattered, so they are noisy, let's say, no? So that's why the misfit is always very high, no? But even being very high, even if it's reduced, this misfit, this is meaningful. So it's significant statistically, no? When you have a mean misfit of, let's say, 30 degrees, and you are able to reduce it to 27 degrees, this is meaningful, no?
Yeah. So we
suggest that in the future you consider also these predictions, no, to have better constraint models. Yes.
Yeah, thank you. But yeah, so I didn't show you the results, but we did look at the horizontal maximum principal stress directions and compared them. I didn't have time to vary model parameters, and I only looked at for a best fit model, but what we find is not good fit with the observations. So, and you're right that it depends a lot on how we are smoothing the observations, because it's in so many. Yeah. So what we've tried so far is just smoothing it on a 1 degree grid, and our mean misfit was about 40 degrees. So it's quite large.
Yes. Yes, but even if it's large, if you are able to reduce it, no, even a small reduction could be an improvement. Okay, so very interesting your talk, and also Juliane's talk. Yeah, very nice. Thank you.
All right, Michael.
Yeah, thank you. So for really nice talk to both of you. For Arushi, so have you tried like using different viscosities depending on if you had a convergent boundary, convergent margin, or divergent on some other kind of margin? And also, have you tried using plasticity, like friction instead?
No. So to answer your first question, not in this study, because we have over 10,000 falls, and it was just hard to isolate the falls which correspond to the plate boundaries, or which are convergent versus divergent. But for the simplified Newell model, we did try using different viscosity for ridges and trenches, and that didn't help us. I know that there are studies which use the inverse of strain rate, observed strain rate, and use that as the viscosity, and that like Ghosh's study, they get good fits, but we've not done that. And we have not used plasticity, no, but that's something we would want to do. Yeah.
I think that would be a way to maybe better have a stress transmission between the plate and the strain rate. Then if you are only using viscosity, you will rely on the resolution that you give at those plate boundaries. Yeah. Okay.
Yeah.
Next talk.
All right, Renee.
Yeah, it's not really a question, Arushi, but can you talk a bit more about how we used SLAP 2? Because that might be of interest to some other users who think about integrating slabs into their models. And then maybe Menno can also talk about how an alternative way to integrate SLAP 2, or like maybe both of you can give a summary of what's currently in the works or what we have been doing.
Yeah, so in aspect, the way we use it is a initial composition. So it's a initial composition plugin in SLAP 2. And what we are doing is using a constant temperature anomaly which is diffused in the slab. So we use a temperature anomaly with respect to the mantle of 700 Kelvin, and then we diffuse it just to represent the slab structure. Accurate oceanic model. That's how we use it.
We essentially created an ASCII data set and read that into the model.
Yeah. So, and I remember that like the way we have it right now, if you want to use just one slab in not all the slabs, like the Python script is pretty easy to modify and use it that way.
Is that already part of the cookbook that you mentioned, or
not
is
the
that...
cookbook, it's the part of aspect. It is in main aspect, but
Okay.
I think it's the initial composition that it's part of and not the cookbook.
Okay, cool. Thank you.
Yeah, so to follow up on the next question, so in the world builder currently, you can make 3D slabs by making slices through the slab, and then defining how the slab is changing. And there's I'm currently working on a new way of doing it, which would better fit slab 2 data, which would make importing slab 2 data trivial, and then you would also be able to extend it, but that's still in the works. All right, Manar?
Hi, thank you both for the great talks. Juliane, I had a question about the core, like once you have core mantle boundary heat flow, you run core models. Given the times of the core mantle boundary heat flux that you're interested in, do you have an inner core for the dynamo models? Because some of them perceived some estimates for the age of the inner core, and I just don't know. I know that a lot of people found that the magnetic field is not so stable if you don't have an inner core, so I wonder if your results are similar or different.
Yeah, so for those models, we sort of what we were trying to do, we were trying to isolate just the effect of the pattern. So we left everything else the same. We even left sort of the amplitude of the total heat flux the same, so that we would only see what's the difference that the pattern would cause. But then separately, I think, so Dan Talner, right, he's the person who ran all of the geodynamo models. He also separately ran models that had a different inner core size. So, right, that's something that we're also thinking about, but we just wanted to look at the two things separately first to see, right, how do they separately affect the models. And so I don't know exactly what he found for the, like, I think he hasn't analyzed the models of the different inner core sizes yet, but you're right. And especially there's no inner core anymore, there's a part of the driving force missing. And so your magnetic field might look really different.
I'll look at the preprints.
All right, do you have any, Michael?
Yeah, just a follow-up question on this slab 2 we were talking about. Is there a way to give like some I don't know, some plate boundaries from a G plate, or we give the velocity, and is there already a way so we could directly like prescribe the slab? Okay, slab 2 will take it from ASCII, but what if we want to prescribe the position of slab like 500 million years ago, or even before that? Like, what's the best way to do it?
I don't know. Yeah. There is a G-plates plugin, but then it has to be consistent with present day slab 2 model, and I don't know how to do that. Yeah.
So maybe
yeah, I think that's a great question, Michael. So the only way we can directly import data from G-plates at the moment is like Arushi said with the G-plates plugin, but that only prescribes velocity. It cannot prescribe features, not like plate boundaries or something like that. What you would have to do at the moment is to export these features from G-plates into some text format that you can then read and reformat into the ASCII data format that Aspect would need as input. And then you can read it in as a composition and modify the material properties of that composition in whichever way you want. It's a clunky way, but it's the only way that we have at the moment. The other approach is to use the geodynamic world builder to define your features in that format. But then you would also need to get the data from G-plates into the geodynamic world builder format and then use that. So either way, you will have to do some manual conversion.
I see. Okay, thank you.
All right. Any other? Oh, go ahead.
Yeah, I just had another idea. If you're interested in that, Michael, the main Gplates format is an XML data format that is relatively easy to read. So that's what we're doing in the Gplates velocity plugin. So as long as you know how that format works, you can use an XML reader and an Aspect to read that file. And then the question is just how do you extract the data in a way that Aspect can use it? So if you're interested, you can take a look at the Gplates velocity plugin. And
yeah,
the tricky part is really just to know the format that Gplates writes and then understand how to change it so that Aspect can use the information.
Okay, yeah, I see. Yeah, I've been using the velocity one plugin, but that's a good idea. Maybe could be another process to write another module.
Yes, absolutely. Would be great. We've been thinking for a long time to at least write a plugin for the initial temperature to use the seafloor ages from Gplates to prescribe kind of like the top boundary layer temperature. But we never really got around to actually writing it.
But if you want to use Gplates to have sort of historic, well, prehistoric locations for faults, for example, then you still have the trouble that Gplates really just gives you sort of, you know, the surface lines of this, even in the past, right? And you don't know if this goes this way or that way. And I think the bigger challenge probably than just to read Gplates and sort of read the plate boundaries in the past is then to figure out what you're actually going to do with it, right? How deep does that trench go? How deep does that fault go? Does it have an angle? All of these sort of questions. So I think there's a lot more interpretation work necessary than just implementation work.
Obviously, like maybe the easiest way for now would be just to have a Gplate on a, let's say you run a global model, you could just give the plate velocity for a few million years until you get subduction, and then yeah, and this will be your initial state. That's maybe
but that we already do, right? I mean, we the models that Juliane, for example, uses, right, does use plate reconstructions like from I don't know if she uses Gplates, but like from Gplates. So you can prescribe past plate motions through the Gplate plugin. It just doesn't prescribe fault locations, right? These faults then have to sort of form by itself.
Yeah.
And I want to add to that, if you either want like the model output or if you want, right, I mean, the input files are like there's a data package that comes with the publication that has all of the input and data files. So if you wanted to, right, I think for something like how did the slabs look like 500 million years ago, a reasonable assumption to say, well, let's just take a model that started 600 or 700 million years ago and then see how they look like and then take something like that. And of course, then it depends on the viscosity structure and all of those things. But I think if you want to test sort of different time frames, that could be a reasonable scenario. So if that's something you actually want to do, to try, and you need other output that's not in the data package, I'm happy to share that with you.
Yeah, I mean, in my case, I want the model to be running by themselves. So, but it's true that I would like them to initiate with a state that makes sense with maybe the state that I want to start with. So, maybe I don't need to be as accurate as what Arushi is doing, but
I mean, right, in that case, you can just take the model with everything, right, the same rheology and everything that you already have, and prescribe Gplates for a given time frame, whatever you need until you think your slabs look reasonable. And then you switch off the surface boundary condition and let them evolve with sort of whatever you apply as boundary conditions at the surface. And then you have a reasonable initial state for that.
Yeah, I had some trouble to switch off the boundary condition and make it free surface then at restart and but so yeah, I can think about somewhere around. Yeah. Thanks.
Is the trouble that you were running the model for a while with the prescribed surface, and then when you switched that off and switched on the free surface, then it would crash. It wouldn't. It would complain.
Yeah.
I think we had this before, and the problem is that internally Aspect only initializes all of the free surface data if you actually start with a free surface, the model, so you cannot just change it during a restart. But I think what you can do, or what might work, is that you start with mesh deformation enabled, but you don't use the free surface as the mesh deformation plugin. You use a function that is just 0 all the time, or an ASCII data that's just 0. So in that case, the internal machinery for the mesh deformation will be initialized and switched on, but the mesh deformation just always stays at 0. And it might be possible to just then, during a restart, replace that function plugin with the actual free surface plugin, and that might work. It's experimental. Don't rely on it, but it could be worth a try.
Yeah, I will try. That's a good idea. Thanks.
All right. It's 35 now. I first want to thank all the speakers again for their great talks, and everyone for asking questions and having a good discussion. So thanks for that. And now we're having a 25-minute break. So we'll be back on the top of the hour. And that's for an optional meeting time. If you have questions or need help with something. Renee, do you want to expand on that?
Yes, I just wanted to say 1 or 2 sentences about it. So the last session today is fully optional. We offer this just to have open time for discussion. If you have questions about how to do something in Aspect, or you have suggestions for what we could do, or if you want to discuss a project with someone, then feel free to stick around. But it's not a very formal program at that time. And I will actually have to miss a part of that today because I have to go to another meeting, but Juliane has agreed to moderate that part. So feel free to be back at the top of the hour, or otherwise, I guess we'll see you all tomorrow for the next presentations and discussions. I want to thank all of the chairs of the sessions and all of the speakers for handling this and taking some effort off of my shoulders. Thank you. See you all later.
And you get our thanks, of course, for organizing all of